All right, so something has to work. So you know that picture. Is this the size, the usual size? There has to be a bigger size somewhere.
Just press the one close to the cross.
Close to what?
The cross. Yes, I recall.
Cross.
Not the cross.
Okay, so the usual picture, and then of course then the usual paradigm. So you all know this business, and the typical dimensions are here. The only thing is that it's you know, even though this picture of internal and external shocks is sort of the simplest to deal with, it seems to work pretty decently with the external shock and the afterglow. In the internal shocks, even though one can do calculations very nicely and a good fraction of them work out qualitatively and quantitatively when you compare it to observations, sometimes there are difficulties in actually fitting, you know, time-scale variabilities, spectral indices and all that in a simple internal shock with Fermi acceleration. So there have been attempts at replacing it with magnetic dissipation, turbulence, etc. And those have been qualitatively all right, except that when you start working numbers, you find that you don't have all the tools for actually building a complete model to start comparing with observations. So one is left still with the internal shock picture, even though one realizes that some elements are missing, but it's still sort of the basic tool that one can use reliably. Now, of course, the basic elements, you can have sort of non-thermal particle acceleration, and then that leads naturally to broken power law synchrotron spectra. And in an internal shock, maybe the break is at MEV energies, and so you get your band function. Or maybe the break energy of the synchrotron is in the optical, and then the inverse Compton component gives you the MEV break, and then you get the GV component from the inverse Compton scattering. And then in the external shock, you certainly have a reverse shock component, which is typically in the optical UV, because you have more particles in the ejecta than you do in the shock interstellar medium. So, the reverse and the forward shock more or less have the same amount of energy, but there are more particles in the reverse shock, so the energy per particle is lower, so the emission is at lower energies. And then the forward shock then is higher energy, gamma ray, etc. Since the compactness in the external shock, the gamma opacity is lower, you can in principle get up to TeV energies. Now the prompt emission in many bursts starting with 990,123 could in principle then be interpreted as the synchrotron reverse shock, and then one would say, that the rest of the emission is internal shocks, the prompt emission is internal shocks, etc. But of course, you could have a situation where you get prompt emission from the internal shocks as well. So one tries to figure that out with measurement with, let's say, Swift, and then cross-ground-based prompt robotic telescopes. Whether the optical light curves behave in the same way, the prompt optical light curve, the prompt optical flash, whether the light curve behaves the same way, let's say, as the gamma rays. And so the black curves is the gamma rays from that, and the, let's say, ROTC light curves, optical light curves, are these crosses. And in some cases, the light curve more or less behaves like the gamma rays. In others, it behaves opposite to the gamma rays. So that was the reason one concluded in the first optical flash that it was a reverse shock. But here you'd say that maybe both of them come from the same shock. So one example where they seem to be doing the same thing was the naked eye burst. And there were at least two different prompt optical detections. So here's the gamma ray light curves in black, and then the crosses are the optical. And so it seems that they come from the same emission region, let's say internal shock. But the radiation mechanism is not obvious, because you have to get, of course, the spectra to come out reasonable, and so you have to explain both the gamma ray spectrum and the optical spectrum. And so these are a complicated burst for other reasons as well. The light curves in the X-ray behave in a different way as the light curves in the optical UV, let's say, as seen by the UVOT on Swift. You see the breaks occur in more or less at the same time, but in opposite directions. So clearly it's not the same shock that's doing the emission in the two wave bands. And some of these breaks are easy to interpret, like a break, you think these are jet break, but then what is these, etc. So and if you look at these in more detail, so here is you get a more complicated thing. You get sort of like two breaks in the X-rays, one break and then another flattening and another break, and same thing with the optical, two flattening breaks. And so in a burst like these, one eventually ends up with the need to consider a more complicated picture, where the model that eventually was settled on was that one had a two-step jet, a narrow central core with a somewhat larger Lorentz factor, and then a wider outer sheet of the jet, the wide jet and the narrow jet. And then, conventionally prompt gamma ray emission, and then you have forward shock and reverse shock in both jet components. And of course, then you have large angle, sort of, the high latitude emission, so-called. And so you end up arguing that, in these jet, then you can, in these composite picture, then you can explain both things, like forward shock, narrow jet component, forward shock, wide jet component, and reverse shock, wide jet, forward shock, wide jet, and then you have to sort of, to make everything work, some components are not seen in the bands of the instrument, but you don't have to worry. I mean, it's all sort of, after you have sort of manipulated the whole jigsaw, everything fits. The only thing is that, nature appears to be complicated, and so the model is complicated, but, so is a BMW or a Mercedes car. So, life, sometimes you have to settle for complications. Okay, so one of the other interesting things with prompt emission is that we know the picture that long bursts arise from the collapse of massive stars, and a supernova is associated with them, and eventually after several days you see the supernova become optically thin. But at some point the stellar envelope has to be ejected, so a shock has to propagate through the ejecta, through the envelope of the star, and so people have been looking for 20 or 30 years for the shock breakout from the stellar envelope, and it was hard to detect. In these bursts, Swift happened to be looking at the region when the burst occurred, so the X-ray telescope was in fact on it, and so it seems that here one has detected the breakout, the shock breakout. because when you look at the X-ray component and the gamma ray component and the ultraviolet optical, what you find is that there is a non-thermal X-rays, and this looks like a sort of conventional, well, not conventional, but the typical Swift X-ray light curve, except that the X-rays here are mostly non-thermal, but here's a thermal blackbody component which grows in time and becomes dominant here at about 10 to the 3 seconds. And here is the equivalent blackbody radius evolving in time and a typical blackbody temperature evolving in time. And so this was interpreted as being the shock breaking out from the surface, not of the star itself, because one needs to fit it with a radius larger than a Wolf-Rayet radius, about 10 to the 12.5 or 10 to the 13 centimeters. So we concluded that these had to be the shock breaking out through the wind of the progenitor Wolf-Rayet star at a somewhat larger radius. And it had to be an anisotropic wind to explain the time scales. It's not just a simple spherical type of picture, but you have to argue that the shock becomes semi-relativistic, and so what you're seeing is the pattern speed as it expands sideways. But it looks pretty much that one has seen here the shock breakout for the first time. Now, when you're accelerating electrons to produce photons, and that picture seems to work, you expect also to accelerate protons, and relativistic protons then will interact with other thermal protons or with the ambient photons, the gamma rays, the X-rays, etc. And then you'll create pions, and the pions will produce muons, and then mu neutrinos, and then electron neutrinos, plus the pi naughts. Then they'll decay into 2 gamma, so you'll get high energy gamma rays. And so this provides opportunities for testing whether, what is the actual proton load of in these shocks. Of course, Fermi and the Air-Cherenkov telescopes can measure high energy gamma rays, and then IceCube and kilometer cube net are already looking, well, IceCube is looking for neutrinos. And other things that you can do is you can test for the Lorentz factor of the shock by looking for gamma-gamma photon cutoffs. And so in the Fermi era, there is something that's being done. And the thing is that once you start thinking about protons, then you say, well, okay, so how can I distinguish between the electron component photons and the hadronic component photons? Of course, the neutrinos are difficult to detect, and so it's easier to detect the photon secondaries. And so if you try to calculate what are the photon secondaries, these are hadronic cascades. You make these very high energy pions and muons, and then the muons radiate, the pions radiate, the positrons radiate, and so you try to see what kind of spectrum you will get, and so you can do calculations, and everything depends on what's the relative amount of energy in the protons, the relativistic protons, and what's the amount of energy in the relativistic electrons. So as Anatoly was explaining, those ratios are predicted by his calculations, but in a more realistic model, one can expect that those quantities vary. And so these are calculations for various ratios of electron to proton, relativistic electrons and protons. And so one finds that in order for the proton components, or for the photons from hadronic interactions to stick out above the electron, the leptonic component, you need to have at least a ratio of electron to protons of 10 or more. So this is all very interesting, but of course it increases the energetics of the burst that you have to put in. So you have to be careful that you don't start demanding too much from the model. And then of course the spectrum also depends on the bulk Lorentz factor. You get more Lorentz boost, etc. And if you then think, okay, but so how is that going to compare, you know, with the leptonic components? Then you find that the leptonic components have a number of things. You can think of simple synchrotron radiation, and then there is synchrotron self-Compton, and then of course you will have the so-called external inverse Compton, because you know you can upscatter the photospheric radiation, and you know you can upscatter photons from internal shocks by external shocks. So you know you can get fairly complicated type of spectral predictions. This is an example from low luminosity gamma ray bursts, where you know you can see a sort of whole plethora of things. Now we're trying now in these after Fermi came up, we're trying to sort of do that type of observations and compare the observations with the models. And of course, Fermi now has been discussed, what its capabilities, etc., are. And this was mentioned briefly. There was this particular LAT burst observed by both GBM and LAT, the one with the largest number of photons so far. It had of the order of 17 photons or so above 1 GeV, and more than 200 and something photons above 100 MeV over 6 decades. And so the interesting thing was that you expect a spectrum with two humps if you have either inverse Compton or hadronic cascade. So a synchrotron spectrum and then a second hump, either inverse Compton or some hadronic component. But these bursts, with this large number of photons, was fitted by just simple band spectra. These are 5-time intervals, so there are the this was discussed yesterday, the 5-time intervals, light curves at lower energies, somewhat higher energies, and then the LAT energy, 2 LAT energy bands greater than 100 MeV and greater than 1 GeV. And so there are these 3-time intervals, 5-time intervals, and the spectra are just plain, uninteresting band functions. The only interesting thing about them is that the peak energy increased first from A to B, and then it's slightly decreased, but then the high energy slope was pretty hard. So initially it was very soft, and then it became hard and didn't soften much in time. So these actually is a GeV afterglow which lasted up to it lasts well into up to more than 10 to the 3 seconds. And the other interesting thing that was mentioned, of course, Julie mentioned is that the peak of the MEV radiation came earlier, and the GeV peaks came like 3 or 4 seconds later. So in the time interval A, there is no GeV emission, but it comes later. There's this time delay, this lag. And so, of course, you can cook up easily astrophysical scenarios for why the high energy radiation would lag behind the low energy radiation. But the thing that captures the imagination is could it be that it's a hadronic effect, even though you don't see it in the spectrum, but could it be a hadronic effect because you expect the cascades to take a somewhat longer time to develop, and those could do the higher energy radiation. But that's really hard because you didn't see a second spectral component to within 1 sigma. Then you can think of various other scenarios, like initially you have a high photon optical depth, which then becomes lower. And so later on, then you can see the high energy radiation, but then you'd see a certain behavior of the spectral index, which is not what it corresponds to. So the situation is complicated, but one fascinating possibility with the lag is that it may be due to perhaps just a propagation effect. The redshift is very high, 4.2. And the differences between 13 GeV photons and MEV is fairly large. And quantum gravity theories are non-existent so far, at least not in any kind of finished form, but one more generic prediction is that you would expect space-time fluctuations which induce something like a time dispersion in the propagation of electromagnetic pulses, also neutrino pulses, such that the higher energy photons would be delayed. So it's like plasma dispersion, you know, to get this dispersion in energy. And so one can, you know, produce a sort of Taylor expansion where you ignore all the details of the theory, but the departures from Lorentz invariance are proportional to the photon energy, to the quantum gravity energy, and then there is, you know, first order n equals 1 or second order n equals 2, etc. If these were 0, these would be just normal Lorentz invariance. So these would be a Lorentz invariance violating term. And so the time delay that you can get from that is determined A by, you know, distance, cosmological effects, and then the difference between the high energy and low energy photons. And then you get these MQGs, the same thing as the EQG. So it's a quantum gravity energy scale. Everybody thinks that's a Planck scale, 1.2 times 10 to the 19 GeV, or something close to it. So you can put a limit on it because you know delta T. And so in first order, the limit is only 1 order of magnitude below the Planck energy scale, which is you know, the best result so far obtained, more than 1 order of magnitude better than any other limit. In second order, the limit is not terribly interesting, but you know, both of them are the best limits obtained so far. Of course, the explanation could be astrophysical. One astrophysical explanation for the delay, something that Kenji Toma and Shuofeng Wu I tried to work out. We did work out something. You consider, you know, that you have a relativistic jet, and then whenever you have a jet propagating out of a star, you also eject a cocoon of waste material, and the cocoon eventually becomes optically thin, so there is a photosphere, and X-rays from the photosphere can be upscattered by the relativistic electrons in the jet, and so, you know, trying to explain these complicated spectral developments for these bursts seen by Fermi, we end up with a scheme where we can fit things if we assume that the jet is emitting synchrotron photons in the optical, and the MEV is caused by first order synchrotron self-Compton, and then the cocoon X-rays are upscattered to 0.3 GeV, and the time lag from, you know, time delays comes out to be of the right order of magnitude. Now, these are the band fit, okay, and this is the plus minus 1 sigma, and this is what the, you know, what the model does. And so, you know, I mean, it's within 2 sigma, you could say the thing is explainable. This is the cocoon, okay, and the upscattered component, and the second order SSC is just below Klein-Nishina, just sort of kills you in time, so that, you know, everything fits within 2 sigma, and you didn't have to invoke quantum gravity, so everybody can you know, breathe out. You know, we can do conventional astrophysics, but it's again, you know, not an easy fit. You have to sort of work at it a bit, and you have to sort of manipulate. This is what the time lag looks like. So as far as time lag, you can explain it just fine. And as a bonus, one can even explain the slope here if you argue that there were additional shocks, you know, which are associated with the second pulse. All right, let me discuss briefly some other aspects then of the proton component. You would expect then the production of neutrinos from protons interacting with gamma rays, the gamma rays produced by the electrons, and you produce these high energy TeV neutrinos or 100 TeV neutrinos. So the first thing you need is you need baryons. If it's just an electron-positron plasma, you will get essentially no neutrinos. And so these would be a very nice test of what is the baryon load of the fireballs. The baryon load, of course, is a direct measure of the Bach-Lorentz factor, which you can sort of measure through other things like the gamma-gamma pair cutoffs. So you would have, but one never has been sure whether the cutoff one sees is due to poor statistics, or it's due to the spectrum maybe cutting off, or is it really gamma-gamma effects. So seeing neutrinos would be the real proof. Now you need to make sure then you have a decent baryon load, otherwise no neutrinos, and then you need target photons or target nuclei. So the environment where you make it produces different energy neutrinos with different fluxes. So typically you need, again, to detect the neutrinos with current things like ice cube, cubic kilometer detectors, you need a decent baryon load. You need an energy in protons which is at least 10 to 20 times the energy in relativistic electrons. And then you might see the diffuse flux from all the gamma ray bursts that occur, out to redshift 3 or 5, whatever. So you would see the cumulative diffuse flux to the extent of maybe getting 20 or so neutrinos per year, which you can associate with gamma ray bursts. If the bursts are very nearby, like redshifts 0.15 or 0.2, then you might see individual bursts. All right, so ice cube is at the South Pole, and so it is a detector whose area is a square kilometer, like that, and it extends down into the ice. So at 1.5 kilometer down to 2.5 kilometers, there are these strings with phototubes attached. And there are cosmic ray detectors here, so you can also measure cosmic ray showers. And now there are about 59 strings out of the total of 80 are already installed, so by 2011 these will be complete. And so the idea is that the neutrino interacts with the proton and then makes a lepton and the neutrino. And the lepton, in the case of a mu neutrino, the muon, is traveling relativistically at a speed which is faster than the phase speed of light in ice, so you produce Cherenkov radiation, and so the phototubes measure the Cherenkov light, and you get a good angular resolution of about less than a degree. And typically the threshold for these Cherenkov tubes is for the setup of these tubes is about 100 GeV, but there is a second component, the so-called deep core, which is going to be put further down deep and more closely spaced, so you can get the threshold down to about 15 or 20 GeV. So one of these strings is already down, and I expect to have the rest down. And so the various situations where you expect to do these neutrinos are, as the shock is propagating through the star, you can have inelastic collisions from the coupling of neutrons and protons in the outflow. Then you can have shocks while the jet is still inside the star, accelerating protons. Those neutrinos would escape as a neutrino precursor. And then when the internal shocks or external shocks happen, then the protons can get accelerated there, and you get neutrinos simultaneously with the gamma rays. So various, well, let me just, these are the decoupling, the inelastic collisions of neutrons and protons. These would produce 40 or 50 GeV neutrinos, and so these was one of the motivations for building these deep core components. And then these are the precursor neutrinos from the jet inside the star. In some cases, the jet might not make it out of the star. In that case, you only see neutrinos. So these would be choked bursts as far as gamma rays, but they're successful bursts as far as neutrinos. So you might see some of these, neutrinos that would have made gamma rays if the jet had come out. There may be actually more of those than those that produce gamma rays. Yes?
How do you accelerate particles in these shocks?
In the usual way, we
No, because these are radiation-mediated shock. I mean, anyway,
No. It's the you get that at the termination shock, but these are internal shocks inside that.
They are still radiation. The optical depth is too large.
No, the optical depth is has been tested there. You're thinking of a different component there. You're thinking of you're thinking of where you have the termination shock. So these internal shocks, and then you have the termination shock. We can discuss it, but we looked at that.
The density is much higher, right? The density is much higher.
You need Lorentz factor. If the Lorentz factor is larger than 200, 300, then maybe. Yeah. But if it's lower, then it's radiation-mediated.
No, I mean, no, we have checked the radiation domination there. So it's, I think these not a problem. We should look into it in more detail, but so it's, I think first of all, the jet is sort of moving more slowly while it's inside the star. So even though the radiation, even though you may be pumping up a relativistic fluid, inside the cavity where the shocks are occurring, the radiation density is such that you don't have these effects. There's still collisionless shocks. Okay, so one other component that you can have is a very high energy neutrino component. In the reverse external shock, the photons are optical or UV, and there they interact with high energy protons, and they produce neutrinos which are in the 10 to the 17 or 10 to the 18 electron volt range. And so there is a Japanese proposal that's going to be put in the space station, which is sensitive to these kind of things. Okay, so time has gone, so I'm not going to discuss these gravitational wave thing. The comparison of multi-wavelength observations at high energy photons and low energy photons is something that is really very useful to constrain models. The more we learn about it, we realize that the models have to become more complicated. But I think the pictures look physically reasonable. There is nothing that is really sort of completely crazy. If one had gravitational wave and neutrino observations, one would be able to constrain things even better. And I think that the problem is that really sort of the leptonic and hadronic components are hard to disentangle, so these have to be modeled very, very carefully. The shock microphysics and in general the microphysics of the generation of magnetic fields that produce the radiation and all that is still in a state where we need to learn a lot more about it in order to do good models. Clearly now that one is observing bursts up out to redshifts of 8.2 or so, the prospects for doing cosmological things like, the 8.2 is sort of the highest confirmed spectroscopic redshift of any object ever confirmed spectroscopically. So now you can say that the most distant object that is guaranteed to be at the redshift plane, 8.2, is a gamma ray burst. So I think one can test things like, what is the earliest period of star formation, and once you get a burst at those redshifts, really, while it's on, the X-ray luminosity is maybe 100,000 times larger than the X-ray luminosity of the brightest Sloan AGN. Of course, the AGNs last a longer time, but for the whole day, the gamma ray burst is brighter in X-rays or optical than any AGN. So in terms of a light beacon for testing the intergalactic medium composition, etc., you get a fantastic tool. Thanks.
Thank you. Questions, please.
Can you mention the gravitational wave thing that was good?
Well, I can mention it, yeah, so the idea was that, you know, you have these flat spectrum X-ray light curves. And so one possibility is that maybe you have a temporary magnetar that's injecting energy. Now, that has some difficulties because you might expect then the breaks or, you know, the changes of the light curve to be achromatic, and sometimes they're chromatic, sometimes they're achromatic. But one thing that you would get to prove or to test whether it's a magnetar that's doing that is that it would have to be a fast rotating magnetar, which then would be subject to you know, distortions. A Moynihan-Taylor ellipsoid would form, so it would emit gravitational waves. And so Alexandra Corsi did these calculations of what would be the gravitational wave emission. Of course, the magnetar would also lose energy by magnetic, by electromagnetic dipole radiation. And so you can make these predictions of the gravitational wave signature, which would last as long, of course, as the flat portion of the X-ray light curve. And so, in principle, these would be detectable by the advanced LIGO and Virgo. So it's, you know, it's a prediction that actually, unfortunately, we will need advanced LIGO, but I think it would be a way of testing whether a magnetar forms there.
In the picture that you have a sketch for these X-rays photon scattering with the relativistic jet. Did you think that the cocoon is left behind when the jet just emerges through the surface of the star?
No, the cocoon was assumed to be expanding afterwards, you know, as at its speed of sound, expanding at the speed of sound, see the square root of 3.
That's what I meant as well. Maybe I misinterpreted the cartoon, but apparently there was a relativistic jet, a core, and then there was photospheric emission from behind.
Right, so the cocoon is more spherically symmetric. The cocoon being semi-relativistic, it expands almost, you know, like a little fireball of its own. It's just less relativistic.
But the jet advances speed when you break the surface of the star is also sub-relativistic. I mean, it's...
Yeah, inside the star is, so this was outside.
Oh, okay.
Yeah.
Questions? Okay, thank you, Peter.